Hello students, welcome back to next session. We are going to discuss the types of compressors used in refrigeration systems. So this session is about completely compressors. So these are all the topics we have seen in earlier sessions. So today we are starting compressors. In next session I am going to discuss condensers. So just we will see what is vapor compression refrigeration system that we have discussed in this unit, and now just I wanted to recapitulate this. Here you can see these are the four major components. The one is compressor, condenser, expansion valve, and we have the evaporator. These are the four major components of our system, that is vapor compression refrigeration system. So here the main functions of these systems are: compressor, it is a machine used to compress the refrigerant from the evaporator and to raise its pressure so that the corresponding temperature is higher than that of cooling medium. So that is the compressor need in our refrigeration system. And condenser, it is an important device used in the high pressure side of a refrigeration system. So here why it is high pressure side is we are getting the output from compressor that we are connecting to the condenser. So here it is important device used in the high pressure side of refrigeration system. Its function is to remove heat of hot vapor refrigerant discharged from the compressor. So whatever heat that is acquired by the air while compressing it, so that will be removed in the condenser process. In throttling device, it divides the high pressure side and the low pressure side of refrigeration system. So here the high pressure side is comprises of compressor and then condenser, and then the throttling device, it is also known as expansion device or expansion valve. So it divides this system into two parts, as high pressure side as well as low pressure side. So evaporator, its function is to absorb heat from the surrounding location or medium, which is to be cooled by means of refrigerant. So this is the evaporator function. It absorbs heat from the surrounding location or medium, which is to be cooled by means of refrigerant, where refrigerant is circulated in the evaporator. These are the four components. And refrigerant compressor, so this is the first component or first device in vapor compression refrigeration system. So here to see the introduction about it, a refrigerant compressor is a machine used to compress the vapor refrigerant from the evaporator. So here the vapor refrigerant from the evaporator is compressed here in the compressor. It raises its pressure to the corresponding saturation temperature is higher than the cooling medium. The compressor continually circulates the refrigerant through the refrigerating system. So compression of refrigerant requires work to be done. So the compressor must be driven by some prime mover. So prime mover should be connected to it. It may be some external motor, that is external electrical motor that is connected to the compressor. So the compressor takes heat at a low temperature from the evaporator, pumps it to the high temperature to the condenser. With a high temperature to the condenser, due to this function, the compressor is often referred to as heat pump. So classification of compressors. So here the compressors are usually classified into three major types. One is reciprocating, screw type or rotary type, and also centrifugal type. So reciprocating type compressors further classified into three groups. So these are actually positive displacement machines where pressure is increased by decreasing the volume of gas. So that is the positive displacement. Positive displacement can be achieved by eliminating the clearance, or otherwise it is called as gap between the shell, that is the casing of the compressor, and the rotary member of the compressor or reciprocating member of the compressor. So here in reciprocating compressor we have reciprocating member. So the main components include one or more cylinders equipped with reciprocating pistons for compression. These compressors can be further classified into three groups. One is open compressor. The motor is externally coupled and accessible for servicing. So it is externally available for servicing. And hermetic compressors. The motor is sealed with a welded steel shell, and it cannot be serviced. It is not available for service. Hence, it is welded permanently. And another one is semi-hermetic compressors. The motor and compressor are housed together, and parts like cylinder head are removable for service. So here the cylinder head and other parts can be removable for service here in semi-hermetic compressors. So this is the compression work taking place on PV diagram. So here this is the reciprocating member, this is reciprocating piston. So piston at bottom dead center and piston at head center. So that is the maximum volume that can be swept from here to here. So this is the swept volume, this is known as swept volume. And the piston at top end, so this is the minimum volume. So this is the top dead center, it is at top dead center, so it is minimum volume. And the PV diagram you can see here. So this is the compression taking place. So volume is getting compressed. So from VC, so this is the V1 and V2, V3. So from V3, so V3 is having highest volume when the piston is at uh, bottom dead center. When it compresses, the pressure increases, the obviously the volume is getting decreased. So when the pressure, otherwise we can say, so this is the displacement. So displacement pressure from P3 to P displacement, and the pressure is getting increased on decreasing the volume. So that is the compression process taking place here. So volumetric efficiencies in reciprocating compressors. The volumetric efficiencies are crucial performance indicators for reciprocating compressors. The two types of volumetric efficiencies are total volumetric efficiency. So this is known as eta Vt, and clearance volumetric efficiency. So with clearance, so that is eta the Vc. So total volumetric efficiency, the total volumetric efficiency is given by the actual volume flow rate divided by displacement rate of compressor into 100. So where the actual volume flow rate is the flow of gas in meter cube per second, and displacement rate of compressor is the volume swept through by the piston during the suction strokes per unit time. So this is the actual displacement rate. So clearance volume, it is defined as clearance volumetric efficiency depends on the re-expansion of residual gas trapped in the clearance volume. So this is the clearance volumetric efficiency. So here it is nothing but the re-expansion of residual gas trapped in the clearance volume. So because the piston will not go and meet the top dead center, there it leaves some clearance gap. So that is the clearance gap will retain the residual gases while compression stroke. The efficiency can be explained using the pressure volume diagram. So that we have seen in earlier diagram. The maximum available volume of gas is V3. So that is the V3, the extreme point we have seen. And when the piston is at the bottom of the piston stroke, the minimum available volume is Vc. When the piston is at top of the stroke, So formula for volumetric efficiency, clearance volumetric efficiency equal to V3 minus V1 divided by V3 minus Vc into 100. So this is from that PV diagram we have seen in the earlier slide. So influence of suction pressure on clearance volumetric efficiency. So when suction pressure is P1, so the residual gas trapped in the clearance volume must first expand to volume V1 before suction valve can open. So suction valve can open, and the gas volume induced would be V3 minus V1. So that is the maximum volume minus minimum volume, and the clearance volumetric efficiency is calculated using the formula that is given in earlier slide. The suction pressure is P2, the induction of refrigerant is further reduced, and effective volume of drawing the gas is V3 minus V2. When suction pressure is P3, then the piston has to travel all the way to end of its stroke to allow the trapped gas in the clearance volume to exit. The clearance volumetric efficiency will be 0. So at this point of P3, the clearance volume is obviously 0%. Performance criteria of reciprocating compressors. The key performance factors are: the performance of a reciprocating compressor is influenced by the vaporizing temperature of the liquid refrigerant in the evaporator, that is suction temperature, the condensing temperature. So suction temperature and condensing temperature both are very important factors, and the load variation impact also will be there. In a practical refrigeration system, the load variation affects the evaporator temperature. Systems operating year round, so that is all the way when it is working all the time, the it experience varying condensing temperatures that impact compressor performance. Normally the condenser temperature is also is an important factor here when the compressor runs all the time. So graphs here, the graphs in the figures are representative of typical hollow carbon refrigerant compressors. So that I am going to show you in coming slides. The specific values are not assigned due to variations with the different refrigerants and compression configurations. So these graphs I am going to show you in coming slides. The mass flow rate and the volumetric efficiency, the evaporator temperature variation, the evaporator temperature affects refrigerant density. The high evaporating temperature leads to higher vaporizing pressure and increased density of the suction vapor. The correspondingly, the mass flow rate increases. So this is the graph. Now you can see here, this is evaporating temperature on x-axis and the clearance volumetric efficiency on y-axis. So volumetric efficiency is taking the this path, and the mass flow rate is taking this path, and the graph shows the relationship between volumetric efficiency and mass flow rate with the evaporating temperature in an ideal compressor operating at constant condensing temperature. So here the key points are point A and point B. So point A, where the mass flow rate is 0. So point B, the maximum mass flow rate and 100% volumetric efficiency. So that is point B. So the clearance volumetric efficiency drops to 0 at high evaporating temperatures. So you can see here at high evaporating temperatures, the volumetric efficiency drops to 0. So that is the graph inference here. So volumetric flow rate of refrigerant, the equation for mass flow rate is M equal to displacement rate into volumetric clearance efficiency divided by 100 into V specific volume. So here M is the mass flow rate. So clearance volumetric efficiency, that is eta Vc, that is in terms of percentage, and the specific volume of gas entering the compressor, so that is VSUC. So next we have condensing efficiency, condensing temperature effects, and here you can see the graph. So this is the condensing temperature and the clearance volume on y-axis. So this is the mass flow rate, and this is volumetric efficiency. On the third axis, the mass flow rate kilojoules per kg per second is taken as third axis. So between these three, we can draw the mass flow rate curve, volumetric efficiency curve. So here this is graph 3, where variation of volumetric efficiency and mass flow rate with the condensing temperature while maintaining constant evaporating temperature. So here we can observe that as the condensing temperature increases, the volumetric efficiency decreases. The mass flow rate also decreases due to this drop in efficiency and constant specific volume at the suction. So work of compression and power requirements. So work of compression, the power required by an ideal compressor can be calculated equal to, that is P equal to M into delta H isentropic enthalpy, where P is the power in terms of kilowatt, M is the refrigerant mass flow rate kg per second, and delta H isen is isentropic compressor work, that is in terms of kilojoules per kg. So this is the graph. Again, we have three axis graph between power, evaporating temperature, and work of compression. And here this is the peak point C, and these are the three critical points A, B, as well as C. The graph variation of work of compression and power with evaporating temperature at a constant condensing temperature. The key observation here is the power requirement is large as low evaporating temperatures and drops to zero when the suction pressure equals to the discharge pressure at point A. So that is the main observation here. The power reaches its peak at point C where the mass flow rate is optimum. So impact of increasing condensing temperature. So this is another graph. So again it is a three axis graph. So work of compression, so that is kilojoules per kg, condensing temperature on x axis, on third axis power. So we have two curves, that is power curve and work of compression curve. So work graph shows the variation of work of compression and power with increasing condensing temperature. So here key observation is with increasing condensing temperature, the work of compression increases while the mass flow rate decreases. The power, which is the product of mass flow rate and compression work, increases and reaches a peak before tapering off. So here the power is reaching the maximum value, so and at the compression work, and increases and reaches a peak before tapering off. And next we have key observations from all these graphs. So evaporating temperature affects refrigerant density and corresponding mass flow rate, which increases with higher evaporating temperatures. So condensing temperature has this impact. Higher condensing temperatures lead to a lower volumetric efficiency and mass flow rates. So work and power observation we can see here. The compressor work and power required are zero at extreme temperatures, both high and low. So refrigerating effect and refrigerating capacity, and the refrigerating capacity formula, so that is delta He. The refrigerating capacity is the product of the mass flow rate of the refrigerant, that is M, and heat absorbed in the evaporator, that is enthalpy. In terms of enthalpy, delta He, that is in evaporator, QE equal to M into delta He. So effect of evaporator pressure, the refrigerating effect increases marginally with increasing evaporator pressure. The increase in valid this increase is valid only if the enthalpy of the refrigerant at the evaporator inlet remains the same. So that is another observation here. And here mass flow rate and reciprocating refrigerating capacity. So the Refrigerating capacity is zero. When the mass flow rate is zero, it increases the rise of mass flow rates. So this is the another graph. It is between evaporating temperature, refrigerating capacity, and refrigerating effect. So three axis graph again, and shows the graph of refrigerating effect and refrigerating capacity with evaporating temperature in an ideal compressor operating at constant condensing temperature. So this is the graph for these three parameters, and we are drawing the curve for refrigerating effect as well as capacity, refrigerating capacity. So with rising condensing temperature, the refrigerating effect decreases because the mass flow rate also decreases with increasing condensing temperature. So another graph that shows the variation of refrigerating effect and refrigerating capacity with the condensing temperature in an ideal compressor operating at constant evaporating temperature. As condensing temperature increases, both the refrigerating effect and refrigerating capacity decreases. So this is the refrigerating capacity and refrigeration effect between these three axes. So coefficient of performance of compressors. So COP formula, we know that the COP performance is obtained from the ratio of refrigeration effect to the power input. So that is COP equal to RE divided by work input. So COP behavior that we see here, the COP progressively increases with the increasing evaporating temperature as the refrigerating effect increases and the compressor work decreases. For the same refrigeration effect, the COP is higher for lower evaporating temperatures. So need for capacity control. So here we have to control this refrigeration capacity also. So that is the reason here is in the refrigeration applications where the refrigerating load is not constant, it is essential to control the compressor's capacity for both operational efficiency and economic benefit. So this is the need for capacity control, refrigeration capacity control. Methods for compressor capacity control, there are different methods that we are going to discuss here. Variable speed motor. So one way to control the capacity by using variable speed motor. A multi-speed or variable speed motor can be used to control compressor capacity. The common practice is using a two-speed motor where at low speed the capacity is reduced to one third or one half of the full speed. The cylinder bypass method. Next method is cylinder bypass method. So one or more cylinders are made effective by bypassing the gas from discharge to the intake of the compressor. So this is the cylinder bypass method, and a check valve separates the inactive cylinders from the active ones with solenoid valves by controlling the bypassing. So by using solenoid valve, we can control this bypass. So next, this is the hot gas bypass method. So this is the condenser, and here this is the compressor. So bypass line is provided here. So now the evaporator is working here, and the solenoid valve is kept here. Solenoid valve is kept here, and this is the bypass line provided, and this becomes the hot gas bypass. And cylinder unloading method, the suction valves of some cylinders are held open and preventing compression. Hot gas bypass method, a simple hot gas bypass compressor capacity control is shown in this figure, and the temperature or pressure of the refrigerant may be controlled by solenoid stop valve in the bypass line. So this is the solenoid valve, so it acts like stop valve also. When a capacity reduction is needed, the solenoid opens the and permits some of the hot gas discharge by the compressor to be returned to the suction line. So during the downward stroke, the piston draws gas from the suction manifold, but on the upstroke, the piston returns the gas to the suction line without compressing it. So next is rotary type or screw type compressors. These are the screw type compressors. It is also known as rotary type compressors. Rotary compressors are positive displacement again. So these are also like piston reciprocating type compressors. These are also positive displacement type. So positive displacement type of compressors are more advantageous than the dynamic type of compressors. The motion of the compressors in is rotary, that is circular, as opposed to circulating linear. So this is reciprocating is linear. So here the reciprocation is that is used in piston type, that is reciprocation type, whereas here we are using only circular type motion. So there are two types of rotary compressors, the rolling piston and the rotating vane type. So these are the two types of piston, that is the two types of rotary compressors. The advantages of rotary compressors: high volumetric efficiency, smaller size and a lighter weight compared to reciprocating compressors, and fewer moving parts, about one-fourth of the moving parts of a reciprocating compressor, typically used in domestic refrigerators, air conditioners and large rotary compressors for low pressure applications in two-stage compression systems. So screw type, so this is screw type compressor. A screw compressor consists of two intermeshing rotors shaped like screws. So one rotor has male lobes and the other has female lobes. And the working principle here, the refrigerant gas is drawn axially into the rotors from the suction opening at one end of the housing. As the rotors turn, the gas is trapped in the cavities between the rotors. So these pockets of gas are progressively pushed towards the high pressure side as the screw rotates. So screw normally rotates at a higher speeds. Unlike reciprocating compressors, compression is screw compressors is continuous. So here the continuous flow rate, or we can say the continuous pressure, can be achieved. So stepless capacity control. So a slide valve at the bottom of the housing reduces the size of the compression volume. Volume slides open, allowing the compressor capacity to be reduced to about 10% of its full capacity. So typical applications are, these are used for large chiller systems with capacities ranging from 175 kilowatt and 3500 kilowatt. So in between this range, these are very much suitable. So this is the two types of lobes. So this is a female lobe and this is a male lobe. And when it rotates, the in between gaps, the gas is trapped and that will be sent to the higher pressure side. So that is the working principle of the screw compressor. It illustrates the male and female lobes, showing how refrigerant gas is trapped and compressed between the lobes of the intermeshing rotors. So these are the two intermeshing rotors. So next one is centrifugal type compressors. So centrifugal type compressors uses a rotating impeller, so that I will show you in diagram, to impart a high velocity to refrigerant vapor. The kinetic energy of the vapor is converted into static pressure in the diffuser, increasing the refrigerant pressure. The centrifugal compressors are high speed machines, making them suitable only for large capacity systems. So the working principle of centrifugal compressor, the rotating impeller increases the refrigerant kinetic energy, which is then converted into static pressure in the diffuser section and rising the pressure within the refrigeration cycle. So this is centrifugal compressor and this is the impeller. When it rotates in this anti clockwise direction, it it flow in. So that is flow in will be sent to the flow out with higher pressure. So this is the centrifugal compression diagram. So shows this diagram shows the flow of refrigerant through the impeller and diffuser, and impeller is shown here, diffuser is not shown here, and demonstrating how kinetic energy is converted into static pressure. So kinetic energy is converted into static pressure here. Capacity control in centrifugal compressors. Capacity control methods, we can already we have seen few methods. Apart from that, in centrifugal compressors, these methods are used. So inlet guide vanes, it modulates response to cooling load. This allows control of the chiller output in the range of 20% to 100% of full capacity. And suction damper, it controls capacity by regulating the amount of refrigerant drawn into the compressor. Impeller speed control, varies the speed of the impeller by adjust the compressor's capacity. So the advantages are ease of capacity control in case of centrifugal compressors, flexible control of the compressor output, the compactness suitable for small to large systems, lubrication is also simple, simplified lubrication as the lubricant does not contact with the refrigerant directly, and the disadvantages are it requires a large number of stages for a high pressure ratios, and develops a compression ratio of about 5 is to 1. So these are the disadvantages, and the compression ratio is lesser than the reciprocating type of compressors. So there ends our compressors topic. In next topic we will see condensers, and these are the reference books, and I have given you one more reference book I have uploaded in your Google Classroom, and please refer that. It is good, that material is very good, and you can rely on that material, students. Please refer that. And obviously we have these topics in almost all books, these because these are the basic components we can see or we can come across in all the reference books. Thank you, students. We stop here. We will meet again. We will see the next topic, that is condensers. Thank you, students.